Hi everybody, we have this video to review some of the integration techniques that we learned in Calculus 1 and Calculus 2. We have 10 problems. We cover various techniques in integration. We will have on the integration table will be on this side, and on this side we'll have some important details about each technique. Right, let's just go to the first one. This is just very simple, the power rule, the first formula on that side. So in order to integrate, we have to put them in a power term. So we rewrite that 2x cubed still there, minus square root of x. Square root of x is x to the 1/2. Of course, we use that formula. So we will write that x to the 1/2. X to the 4th, move it up, becomes x to the -4. 5 is a constant, still there. Right. And now we just integrate term by term. X cubed will be x to the 4th over 4. 1/2, increase the power by 1. Divide by the same thing. Increase the power by 1, minus 4 plus 1, minus 3 over minus 3. And 5 is a constant. Integral of a constant will be 5x. And plus a constant c. So that's what we have. Right, we just need to divide by a fraction. We turn that into reciprocal. So we have 2 over 4 give us 1/2 x to the 4th minus 3/2 becomes divided by 3/2 becomes multiplied by 2/3 x 3/2. This divided by -3 will be minus 1 over 3 x to -3 and then plus 5x plus c. Right. So that is the first one. Pretty simple power rule. Right. I'll just move to the next one. Right. Right. On this one, this is classifying one of the problem. It will be very difficult if we haven't seen that before. If we see that one time, it will be very easy. Does not involve any technique at all. We just need a little trigonometric identity. So need some of this. By the way, I throw in the hexagon. This hexagon, it just helps us to memorize these identities. For example, if we put the tangent on the top, and then so we just have like this tangent on top, we will have sine over cosine is a ratio, or secant over cosecant, or 1 over cotangent. So tangent is equal to sine over cosine, secant over cosecant, 1 over cotangent. We can also turn that around like this, and we have cosine on the top, then cosine equal to cotangent over cosecant, sine over tangent, and 1 over secant. And also on that hexagon, we have cosine square plus sine square is 1, 1 plus tangent square is secant square, and cotangent square plus 1 is cosecant square. So, on the basic identities, and of course there will be a lot more, some more useful than the other, but we will definitely see the power reduction. This we use a lot, so we can integrate. Right, get there later. But first, let's go on this one. Like I said, if we haven't seen the solution, it will be very difficult. But once we've seen that, it's so rather obvious. So the trick for this problem is that we multiply by the conjugate 1 minus cosine x, which means 1 plus cosine x. Right, that is where we multiply the bottom. It is the bottom of 2 squares, the difference of 2 squares. So the top is 1 plus cosine x. The bottom is 1 minus cosine square. And now we see why we have to do that. 1 minus cosine square, obviously, it is the Pythagorean identity, so that would be sine square. So I will rewrite this. 1 plus cosine x over sine square. Alright, almost there. What we do after that is we're going to split this. So we have 1 over sine square plus cosine over sine square. Cosine over sine square, I will write like this. Cosine over sine, and then 1 over sine. That will give us sine square. Uh, 1 over sine is cosecant, and that is the square, so we have cosecant square plus cosine over sine is cotangent, and 1 over sine is cosecant. Now the integral cosecant will give us negative cotangent x, and cotangent cosecant, or cosecant cotangent, give us negative cosecant x. And that's what we have. Like I said, without this trick, this will be a little bit difficult because it is not a substitution problem. Right. So we haven't used any substitution yet. Right. The next one we'll use the substitution. So this is the problem. So what we use is the substitution. Let's go to the substitution technique. Of course, the substitution rule is there. I'm sorry, that direction. We need to know what is u, and then we solve for the x. So we'll let this equal to u. So let u equal to 2 plus 5x. And then we solve for the x, meaning we have to take derivative. So if that is u, we take derivative. 5x is 5. Multiply the dx. And then divide by 5. So two important components in substitution is u and then dx. So we have u and then this is dx. And then we'll substitute everything back into the original integral. 19 will still be there. The bottom is u. Dx is du over 5. Right. Now we have no x left, which is good. This constant on the top, 19, we'll take it outside. This is also a constant, 5. I will take it outside. So we have 19 on the top and 5 at the bottom. That will be a constant. After that, we just have 1 over u du, which will give us ln of absolute values of u, and then plus c. And u we substitute back into using 2 plus 5x. Right. And so that's what we have. So this is a standard substitution problem. Right, moving on. Right. So this also substitution. The reason we say that this is a substitution because if we let something equal to u, like the exponent here, derivative of that will be here to cancel. So again, we need to know what is u, which is the exponent. In this case, and then we'll take derivative to solve for dx. So u is that we take derivative of cosine is negative sine, so we have negative 2 sine x. Move the dx over, and divide by the negative 2 sine x. And we found dx. We will substitute back into the original problem. We still have 3 sine x, and then we have a. The exponent is going to be u. Dx is du over negative 2 sine x. Right. If everything works out perfectly, we have no more x. So the sine x do cancel out. Take the 3 outside, the 3 on the top. The negative 2 is a constant at the bottom. Stay at the bottom. So 3 over negative 2. Pretty much everything cancel out except for e to the u and du. Pretty simple. A to the u is still a to the u plus c. So we have negative 3 over 2 a to the 2 cosine x minus 1 plus c. So we test that. So standard substitution. Right. So for substitution, we need to know u. We need to have, so for the x, if everything works out perfectly, there will be no more x, and we integrate in terms of u, and at the end substitute back in for x. Right. The next one going to use different ways. The first one, we can use substitution. You can also use iteration by parts, but just use the substitution first. So substitution, there's a few choices. If we let u equal to x, that doesn't have anything. However, if we let u equal to ln of x, derivative is 1 over x, which is good. It might cancel with this x. So this is going to be u, and dx is going to be dx. So let u equal to ln of x. Now we'll take derivative. Will be 1 over x. Cross multiply, we have x du equal to dx. So dx is x du. So we found u and we found dx. Right. So now we have ln of x, that's going to be u over x. Dx is x du. X and x cancel out. Just have u du. Integral is going to be u squared over 2 plus c. Or we have 1 over 2 u squared. U is ln of x. Right. So this is the solution using the substitution. Pretty simple. We can also use iteration by parts on this one. So yeah, so that is iteration by parts. Let's write a line here. So iteration by parts, we're going to have like that. Iteration by part, u dv equal uv minus v du. Or we can also use the table. We use a table in the next examples. This one we just use this directly. Right. So let's start with the problem. ln of x over x dx. Right. Of course, we need to identify what is u and what is dv. And over there, you see that we have log, inverse trig, algebraic expression, trig, and then exponent. We choose u to be in that order. So let me write down. So we have ln of x right. So let's see. On that list, we checked first. There's log. So yes. So that will be u. If we don't have log, we go to inverse trig, and then we go to algebraic expression, and then trig, and then exponent, or in that order. So in this case, this is going to be u, and this is going to be dv. So let's write out here. U is ln of x, dv is 1 over x dx. Derivative of ln of x is 1 over x. and then dv is that, so we take integrate 1 over x, give us ln of x, absolute values of x, but just have ln of x. The reason being, if this one is defined, that has to be defined as well. So right, so iteration by parts. Now we use the formula. So it's going to be, let me just write the formula first. uv minus integral of v du. So u ln of x, v ln of x. So that gives us ln square, which is good. V is ln of x, and du is 1 over x dx. So pretty much we have ln of x squared minus ln of x 1 over x dx. Well, that doesn't help us much because this is exactly the same as the original problem, but that actually helps us. So let me just write out ln of x 1 over x dx. Since these two are the same, I'm going to add this to that sign. So we'll add ln of x 1 over x dx. Add that on both sides. So we have 2 ln of x 1 over x dx equal ln of x squared. Of course, we can add the constant c somewhere, or just keep the constant c at the end, and then we just divide by 2. So we have ln of x 1 over x dx equal to 1/2. Divide by 2 on both sides, and then we can add the constant c, and we see the solution using substitution or integration by parts will be the same. Of course, integration by parts we can also use the table, but not necessary in this case. Right, so that. I'll go to the next one, which also use integration by parts, but this time we use the table. So first, if we use the table, I want to have 2 components. The first one is u, the other one is dv. So for u is whatever we differentiate, and then we have dv, just v is whatever we integrate. Right. So the choice of u, let's check again. Oops, I want to do that. Right, first, log. We have no log. We have no inverse trig. We have an algebraic expression that is the x squared. So any polynomial classified in that case. So that will be u. Right. Now, this is to be differentiated. So we take derivative x squared. Derivative is 2x. Derivative is 2. Derivative is 0. And if we keep going, still 0. So that doesn't do much. Integrate is going to be e to the 2x. So this is going to be v or dv. And this is going to be u. Now this we integrate. Integrate e to the 2x will be 1 e to the 2x, which is the same. And then we divide by 2. And then we divide by 2 again. Give us 1/4 e to the 2x. Divide by 2 again, 1/8. and 1 over 16 e to the 2x. So 1 we integrate and 1 we differentiate. Right, u to be differentiated and v to be integrated. Right, now we do the diagonals. The first one is going to be positive. The next one is negative. The next one is positive. The next one is negative. And everything after that is going to be 0 because we multiply by 0. So pretty much we just have the first three. So we just need to write out x squared times that. So we have 1/2 x squared e to the 2x. That's the first one. Next is going to be minus 2 times 1/4 is 1/2 x e to the 2x. And then the plus 2 and 1/8 is 1 over 4 e to the 2x. And that's it. So just plus the constant c. So it would be very nice if we can just do that, especially something that vanished to 0. So we use the table is a lot quicker way to integrate iteration by parts. Right, next one, a little bit more complicated. We still use the table, slightly different, but still use the table. Don't need to be that long. So u to be differentiated. Differentiate. And then the v to be integrated. So we'll just check. For u, there's no log, no inverse trig, no algebraic expression. Next step is the trig function. So that's going to be cosine of ax. That should be enough. So derivative of cosine ax is going to be derivative of cosine is negative sine. But then the derivative of ax is 8, so we have negative 8 sine x. Derivative of that is 64 cosine of ax. Negative 64 cosine of ax. And then multiply another 8. That's good enough. And then this e to the 3x integrals 1 over 3 e to the 3x, 1 over 9 e to the 3x, and then so on. One thing we see that this is not going to be, none of them go to 0. We could go on indefinitely, but let's not do that. So we have the diagonal, so it is good. And then next we have another diagonal. So the first one is the plus, the next one is the minus. We could go on forever. However, what we see here is we have cosine and then e. So pretty much we get back to the original. So we cannot just go diagonals indefinitely. We stop at this stage. So we stop using the horizontal line. The sign still alternate plus, minus, plus. Right. So now we write. First, those two will be 1 over 3 e to the 3x cosine ax. Next, it's going to be minus because of the second diagonal, and another minus make it a plus. A times 1 over 9, a over 9, e to the 3x sine of ax, and then plus both. Okay, that's just a plus, and multiply this two, you have negative 64 over 9 e to the 3x cosine ax. I should write smaller. Right. How will we write this? 1 over 3 e to the 3x cosine ax plus a over 9 e to the 3x sine of ax minus 64 over 9, the integral of e to the 3x cosine ax dx. Even though that we get back to the original problem, but that is actually what we want. What we do is, this is on the left side, this is on the right side, we're going to move this to that side. Well, pretty much we did just like the previous problem where we add the same thing on both sides. We do exactly that. 64 over 9 plus 1 is 73 over 9. So we add that to the other side. Give us 73 over 9 e to the 3x cosine ax. Sorry, I need to write a bit smaller. And then this 2. Right, and then multiply the reciprocal 9 over 73 on both sides, and we have that. So e to the 3x cosine ax equal to 9 over 73 1 over 3 e to the 3x cosine ax plus a over 9 e to the 3x sine ax. Of course, plus a constant c at the end. Right. We can also multiply the 9 inside to simplify with this 9 and the 3, but we don't have to do that. So the point here is integration by parts, one to be differentiated, one to be integrated, and just do the diagonal. If we have to stop, just draw the horizontal line, but we still have the integral on that case. The diagonal, we don't have the integral. The horizontal line, we have the integral, and that's what we have. Right, next. This one, just plain trig. So this is just integral of a trig function. So pretty much what we have, the rule of thumb here. So depends if we have sine and cosine, whatever have the odd power, we're going to let the other one to be u. So since we have the odd on the cosine, u is going to be sine. So we know for sure because when we have cosine and sine, whatever has the odd power, we take the order function to be u. Right, so typical du equal cosine x dx, or du over cosine x is equal to dx. So that is dx. We can almost do like what we did before, but we need to have one cosine left to cancel with this cosine. So we can write like this: 8. We need one cosine by itself to cancel with this cosine. So we have cosine, and then to get the cube we have to have cosine square, and then sine square, and then dx. So because we need the cosine x to cancel, so we split out one cosine, and then we have that. Cannot touch the cosine x here. The cosine square here, we use the identity. This one equal to 1 minus sine square x. And then we have sine square x dx. Now we can use the substitution. Have 8 cosine of x still there. 1 minus sine square, that is going to be u square. The sine square here is also u square. Dx is going to be du over cosine x. And that's why we, when we have the odd power, we need to have one left, so that we cancel out. So we have 8 multiplied out u square minus u to the 4th du, pretty much au square minus 8u to the 4th. So that will be au cubed over 3 minus 8u to the 5th over 5. Let's see. U is sine x. And that's what we have. Right. A lot of things that go into this, but if we have an odd power, let make things much easier. If we have all even powers, we have to use power reduction identities. We have to use this. Right. Look like we're going to have that for the next problem. Right. Next is this one where we have to use the trig substitution. Right. For trig substitution, we follow that, and we see that is look like we have a constant minus x squared. So look like that's what we're going to use. So we let u equal to a sine theta. 49 is 7 squared, so that will be 7 sine theta. So let x sorry, that typo here. This is supposed to be x. There's no u here, so this will be x. So in this case, we let x equal to 7 sine theta. Then we take derivative. Seven cosine theta d theta. Everything's ready. We just need to make a substitution back in. Right. Square root of 49 x is going to be that. So we have 7 sine theta square, of course. Dx is 7 right. So we have 49. 7 squares also 49, so we can factor out 49. 1 minus sine square right. One little things, when we do the Trig substitution, there's some certain condition for x. We need to have I didn't have that in the paper because we run out of space. But in that case, this will be just cosine square and square root cancel the square, even though that's not perfectly correct. So 49 cosine square which gives us cosine. In perfect world, we should have the absolute values here. But I assume that all the conditions are satisfied. It gives us 49. Right. Now we have a little problem. Cosine square, unlike the last problem, we don't have an odd power. So if the power are even, we have to use the power reduction. Will be this one. So be 49 1 plus cosine of 2 theta over 2 d theta. Right. So 49 1/2 plus 1/2 cosine 2 theta. Right. There will be a lot more to this. We just integrate this first. 1/2, that's the constant. We just stick the theta into it. And integral cosine is sine. However, there's a 2, so we have sine of 2 theta divided by 2. Right. So we have 49 over 2 theta. Sorry, it's a long problem, so I have to write a little bit smaller. Plus 49 over 4 sine of 2 theta plus c. Right. Obviously, we need to go back to sine, cosine. I mean, in terms of x. But especially the sine of 2 theta doesn't help. We have identity, so I just need to put that somewhere. First, sine of 2 theta is 2 sine theta cosine theta. So that is the double angle identity. We're going to replace into that. Right. Now we need to write back in terms of x. Right. So that from the original, we have x equal to 7 sine theta. So we have sine theta equal to x over 7. So pretty much that's going to be x over 7 for theta. sorry, not. So theta equal to sine inverse of x over 7. Sorry, it should be that because this is just theta. So yeah, that's going to be theta. Now the sine theta, so this is going to be x over 7. We need to know what is cosine. To figure out what is cosine, we have to draw the triangle using this identity. Sine is equal to opposite over the hypotenuse. So with respect to this angle, opposite is going to be x, hypotenuse is 7, and the equation in that case will be 7 squared minus x squared. After that, the cosine is going to be equal to equation over hypotenuse. Right, so we have cosine theta equal to that. So yeah, pretty much we substitute into this problem. We have 49 over 2. Theta is sine inverse x over 7. And then 49 over 4 times 2. Sine theta x over 7. And then cosine theta, that. Plus the constant c. Right, there might be something to cancel. Not the first one though. So I use this for page number. 49 over 2 sine inverse of x over 7. Uh, 49 will cancel with 7 and 7. 2 and 4, so that's just 1/2. So pretty much 49 over 2 sine inverse of x over 7, 1/2 x, square root of 49 minus x squared, and then plus c. Right, sorry, a little bit long. So that's pretty much on the trig substitution. The trig substitution, we using this rule. Sorry, but this will be x instead of u. Right. That will be the last one. This I did not put anything in the technique because this one will involve partial fraction. For that, in order to solve the system of equation easier, we use a calculator. So first, partial fraction. So we're going to split this into a fraction. There will be a lot of rules for the partial fraction. I just do the simple one. When we have the repeated factors, there will be a lot of things go into this. But pretty much we have two factors, x minus 7 and x squared plus 5. We have none repeated, which is good. Alright, x minus 7, the top must have less power than the bottom. So this has the first power, so we only can afford a constant on top. This is the second degree, so the top degree must be less than 2. So we can use the first power, so it's going to be that. If we do the common denominator, then the top need to multiply by a by x squared plus 5, and the bx plus c multiplied by x minus 7. Right. And now the bottom are the same, the top must be the same, so we write 5x squared plus x plus 18 equal to, and I will multiply this out. Just write like that first. So multiply this out. Bx squared minus 7bx plus cx minus 7c. First we would look at all the second power. Will be this and this. So we have 5x squared on this side. We can factor out the x squared. Next, looking for the x. And we have an x here and an x here. So negative, then straight. Negative 7b plus c x. And then a constant. I still have different colors here. So just do 5a minus 7c. So pretty much we just match the coefficient of the same powers. So we have the system of equations. So a plus b equal to 5. Negative 7b plus c equal to 1. 5a minus 7c equal to 18. Right. This I use the calculator. I put in the matrix the coefficient a, b, and c would be 1 for a, 1 for b, 0 for c because there's no c, 5 that no a, negative 7 for b, 1 for c, and 1, 5 for 8, 0 here, negative 7 for c, and 18. We just use reduce row echelon form. So calculator. Actually, I did that earlier. Right, let's zoom out. Right, so full screen here. Right, so second matrix. Actually did this earlier. So 3 row 4 columns, and we just enter this matrix in 1 1 0 5 0 negative 7 1 1 1 5 0 negative 7 and 18. Yeah, so pretty much that. And then quick, go to the matrix again, but this time go to math, option reduce row echelon form, and we apply that to the matrix A. I think I entered something wrong. Let's check again. I did this before to make sure the numbers correctly. So 1 1 0 5 negative 7 1 1 1a, I mean 5 8 0 negative 7 and 18. Yes, I have to do this before to make sure the numbers work out perfectly. I don't want to deal with fraction on this one. Anyway, yeah, much better. Right, so obviously this is going to be A, this is B, and this is going to be C. So the original problem we have 5x squared plus x plus 18 over x squared plus 5 x minus 7 it will be equal to A is 5 x minus 7 plus bx, b is 0, c is 1 x squared plus 5. So we integrate, so we can integrate. Right. We split this into right. This we can use substitution, but this is 1 over something, so that will be just 5 ln of x minus 7. And this one, if we use, let's see, this formula, we can have 1 over a will be square root of 5 tangent inverse u, which is x, square root of 5 plus c. Of course, we can use the Trig substitution again, but that, of course, we can just use the formula, but the one that I highlighted. So that's pretty much it. There will be a lot of things that go into integration. It usually takes a few months to learn about all of this technique, and we have only 10 problems, so that's all we have. Of course, this I think is going to be a good review, or at least we just get the idea of how I do some certain problem. So how do we do substitution or integration by parts, or in this case partial fraction. But anyway, I think this will be a good review for all the integration technique. Thanks for watching.